everybody. How's everybody doing this evening? Good. Okay, so as you guys can see, I'm holding something in my hands here. These are socks. Okay, so I'm having an interactive talk where I like to give out socks for people interacting. And there will be 8 questions in the slides, but the first question that I like to ask is, who knows what LLM stands for? Don't shout it out. I was going to give a sock. Okay, sorry, can't use that one. All right, let me also get a show of hands. Who knows what a vector database is? Okay, that's okay. Who knows what Milvis is? Okay, so my goal is to have people who know what Milvis is and have people who know what vector database is do the same thing. I work on Milvis, so that's why. So today we're going to be talking about how to build LLM maps at scale, and the first question will get some socks. So a little bit about me. I use that. I'm going to use that. Hello. Better? Okay, this is better. Okay. Cool. So a little bit about me. My name is Yujian. I'm a developer at Azulus. I started my career working at IBM when I was 16, and I went to college and I studied machine learning. Published a couple of different papers. One of my papers got into artificial big data here in Seattle, and that was actually how I ended up here in Seattle. Is because I ended up working at Amazon. Someone saw my presentation. They're like, "Hey, you should come check this out." So that's a little bit of background about me. After I was at Amazon, I went to startups. It's kind of how I am where I am now. Today, we're going to be talking about a primer on LLMs. So I'm going to cover some neural networks and like architecture for GPT. Then I'm going to talk to you about how you can work with LLMs with your data, because that's pretty much what everybody wants to know. I'm going to introduce CVP, which we at Azulus call the LLM stack. If you guys are familiar with Mean or MERN or LAMP, this is kind of your replacement for LLM maps. And then I'm going to talk about vector databases, because really I'm going to be talking to you about vector databases the whole time, but I'm just not going to tell you what they are until the end. Okay, so I'm going to give out a sock for this one. Can someone tell me what this is? What is it the architecture of? What is it drawing up? Okay, you right there. This is close enough. I was just thinking for neural network, but I mean that's an even more like technical thing. So this is a neural network, right? You give it some input, it has some hidden layers, it does some calculations, it gets an output, it's using some sort of classification, some sort of prediction. Anyone, who here has taken a machine learning class, like intro to machine learning? Okay, so you guys know what this is. I'm going to breeze over this part. Okay, recurrent neural networks, right? Everybody knows this is for natural language processing. You have sequence paths. You want to work with, words and tokens over time. What you do is you essentially do this recurrence relation where you feed in your output back into your input, with some modifications. So these are RNNs. These are basically made for natural language processing, and these have a problem of not being able to get context over a long period of time and not being able to really understand long inputs. So we have an introduction to transformer models, which really solve this transformer like sequence transduction. Transformers allow you to do sequence-to-sequence transformations of different lengths, different sequence lengths. So this was a real breakthrough in the field. We can now kind of translate things without having to pad the inputs. They didn't have to pad the outputs. You got a really nice architecture here. And transformers consist of an encoder, which gives you a hidden state, and a decoder, which decodes that hidden state. And basically, the encoder is like let me formulate a state from an input, and the decoder is let me guess what the next word is based on the state. And that brings us to GPT. So who here has heard of GPT-3? I said all hands to go up. Yeah, okay. So GPT-3 and GPT 3.5 and all the GPT models are decoder-only architectures. And so what that means is, what they're really doing is they're taking some sort of state and they're predicting what the next word is. So all these models are doing is they're just predicting things. Okay, they're stochastic models. Keep that in mind. These are stochastic models. They're not deterministic. They don't know what's going on. And part of the reason why these LLMs have some issues with their data, as all neural networks have issues, is that the way that they're trained is on a very high-dimensional scale of this. So this is a 3D representation of gradient descent. Obviously, you're never going to work with a neural network that only works in 3 dimensions, but this is a useful example to understand how this kind of works, right? You have some sort of high dimensionality curve, some sort of high dimensionality field, and you start somewhere, you randomize your weights, you start somewhere, and then you kind of go down, and that's your local optimum. That's kind of, what people call well, this is what happens when you have your trained machine learning model. You're at a local optimum. Okay, so LLMs, what can LLMs do for us? Pretty simple. They can automate starter tasks. They can streamline your information retrieval. They can do basic logical reasoning. They can't do a lot more outside of this. They do have this kind of like magic pill feeling to them, but that's not really how they work. This is what we can do with them right now. I'm not saying we can't do much more complex things in the future. The challenges with LLMs, and this is really what I'm going to be talking about for the rest of the time, so you want to pay attention here. The challenges with LLMs is they lack domain-specific data. They don't have data from your enterprise, your company, your project, or whatever, your data. They don't have it. Number two is that they have a lack of up-to-date data. Does anybody know when GPT-3 was trained still? When was the last date that? Oh yes, you go back there with the mask.
March 2021.
Okay, you right there with the red shirt. Oh, there you go. All right. And then the number 3 problem with these is that they consume a lot of resources, right? They're expensive to call, inference is expensive. You gotta have A100s, H100s, all that kind of stuff. All right, here come the pop quizzes. Pop quiz 1. Neural networks such as large language models are A, stochastic, B, deterministic, C, anachronistic, or D, monopolistic. Who wants to raise their hand? The guy with the guy with the white shirt and orange. Huh? A, okay, cool. Pop quiz number 2. I'm gonna have this up while I'm throwing this stuff out there. If you use an LLM out of the box, you may struggle with asking it questions about your data, asking it questions about things that happened before its training data was being done collected, asking it questions about your favorite spot or your favorite sports team, or both A and B. Who wants to raise their hand? Who wants to raise their hand? 3.
A.
Yes, there you go. Why is it not B? Yeah, I tried to trick you guys there with that A and B. Nice catch. All right, so LLMs in your data. Oh, because B said trained on data before or B said asking questions before its training data was done. Okay, so this is a very common and very high demand kind of application right now. Enterprises want to be able to chat on their data. They want to know what's going on with their data. And let's say you're an enterprise. So this is kind of just a setup for you to understand what I'm going to talk about for the next few slides. Just think about, you have hundreds of thousands, millions of documents, you want to query them, you want to know what's going on. Right now, you just have people searching through them, but a better solution would be if you had ChatGPT for your internal documents. We have a technical problem. I don't know.
Did you almost plug in from the computer?
No signal. Oh, it's back. Okay. I'm not going to step over this area anymore. I'm going to be careful here. So where were we? Ah, yes. Why spend hours training your own internal data when you can just ask ChatGPT about it? You don't want to do that, right? So in order to motivate how this works, what I'm going to do is I'm going to sort of explain the concept of semantic similarity. This is a very, very toy example. Once again, don't take this very seriously. You're never going to work with 2-dimensional vectors in production. But for this example, you're going to have these 2-dimensional vectors that represent these 4 words: queen, king, woman, and man. And the idea I want to impart here is that these vectors allow you to do math on words and images. But right now we need words. So first thing I'm going to show you is this queen minus woman plus man equals king thing. So if you start with these numbers here, you kind of see, you know, queen is 0.3, comma 0.9, woman is 0.3, comma 0.4. You do some subtraction here, you end up with 0, comma 0.5. What does this mean? This would probably be something like royalty. You know, what is queen minus woman? The next step is now you add man. You add the value of man. Man is 0.5, comma 0.2. You add that to 0, comma 0.5. Now you have king of 0.5, comma 0.7. So once again, this is a very toy example. Nobody ever works with two-dimensional vectors, but this will kind of give you an idea of how semantic similarity works and how vector similarity search works. Also, I want to touch that you're never going to use Euclidean distance in your vector similarities, but that's what I'm using here. So how are these vectors and embeddings generated? Where did this come from? Really, what they come from is the second to last layer of your neural network. So in this slide, I give you an example of a neural network, and I'm circling the second to last layer. All I want you to know is vector embeddings come from the second to last layer, which means their dimensionality is dependent on the dimensionality of the neural network. And the reason why these are important is because 80% of the data that we have out there in the world right now is unstructured data. The only data that is structured that you have is probably sitting in your SQL database somewhere. So all the data that's generated is pretty much unstructured. And how do you work with unstructured data? Nobody really knows because it's hard, because it doesn't fit a structure. And that's why we have vector embeddings. You turn it into a vector embedding, and there you get your structure for your unstructured data. And then the way you work with it is you put it into a vector database, such as Milvis or Billis. Okay, vector embeddings allow us to A, do math on words, B, do math on images, C, do math on videos, or D, all of the above. Orange shirt, you're the first one I saw. Woohoo! You're gonna get a sock. I'm sorry. Okay, vector embeddings come from applying the Fourier transformation, taking a partial derivative along the dimensionality of the first eigenvalue, or the second to last layer of a neural network, or any of the above. It's a trick question. It's a trick question. Okay, guys? Hope you're paying attention. I saw hands go down. No, your hand is up. What is it? You are, wait, what?
I'm taking a partial derivative.
Your hand. You got it. Okay. Okay, now let's talk about CVP. Oh, I keep pressing the down button. CVP, this is the LLM stack. This is the stack that you're going to build your LLM applications on. C. Actually, this is on the next slide. The key idea here is that we can view LLMs apps as a general purpose computer, right? Kind of applications are kind of built like this. They have some sort of processor, some sort of storage, some sort of interface. So what we did was we said, let's break this down and let's apply this to LLM apps because, well, you know, this is a framework that applies to pretty much most applications. It probably applies to LLM apps. And so it kind of does. What we have here is C, which stands for ChatGPT like LLM, ChatGPT or any other LLM. I have told the team internally that maybe it'd be better to be L, but LVP sounds kind of weird. V stands for vector database, such as Milvis or Zillit. And P stands for prompt as code. And the prompting is the way that you interface between your vector database and your application and your LLM. Okay, so CVP is basically the stack that you're going to be using to build LLM applications for the foreseeable future. This is a demo. I'm not going to actually do the demo here, but if you want to figure out, kind of see an application of how this works, see an example of how this works, check out osschat.io. What it does is it takes open source documentation and it creates an application that allows you to chat with open source documentation using a chatbot-like interface. And you can like test around and like play around with it, ask the things that like ChatGPT won't know. Like I'll ask you things about like AutoGPT. Who knows what AutoGPT is, by the way? Nice, nice. Yeah, that was a huge project. But anyway, yeah, that's not on ChatGPT because it's after the cutoff date, but it is on here. So play around with it, check it out. This is the architecture for one of these applications. Okay, let's just we're going to take the CVP stack and we're going to dive into what the architecture actually looks like. So the first thing that you really want to do is you want to take your embeddings. You want to take your documents, your text models, your documentation. This could be in the form of JSON, this is going to go text, markdown, whatever your documentation is for. You want to chunk it up so that it makes sense. Context-aware chunking is a big thing right now. It's not really solved, but it's a big thing right now. And then you want to put that into a vector database. So actually, there's a step that we left down here, but what we actually do is we actually create a question space. So we ask ChatGPT to come up with questions that might be asked about the answers. And that's a little hack that gives you a better platform. And then once it's in the vector database, once the user queries it, right, step 3 up there, user queries it, we query the vector database. If it's in there, we'll give you the answer, like, structure with ChatGPT. If it's not in there, we'll go to ChatGPT and we'll say, like, hey, maybe you have the answer to this. And so this actually is I guess, like a hyperparameter that you can tune with building your own applications. The reason that I bring this up is because we actually spun out this tool called GPT Cache out of this, because we found that we were running up our OpenAI bill like crazy, creating like questions. And so we were like, maybe we should cache some of these questions so we don't have to like recreate them. Doesn't that make sense? And so that's what GPT Cache is. And this is actually, as far as I know, the only open source semantic cache of its kind. Pop quiz number 5. The C in CVP stands for ChatGPT like LLM, computer, cats, or cosine. I think I saw the guy in the green shirt have his hand up first. You sure?
Yeah.
Yeah, okay.
It's pretty different. Like,
A vector database like Milvus or Zillus can be used as a semantic cache in your LLM to inject domain-specific data, to inject recent data, or for all of the above. I think I saw you raise your hand first, the guy with the hat backwards. Huh? D, all of the above, yes. All right, I don't think I can go that far. No, I'm going to pass it back right now. Pass it back to him, please. All right, so let's take a look at vector databases. How do they work? I've been talking to you guys about vector databases this whole time, and I haven't said anything about what they are. Vector databases are essentially somewhere where you store your vector embeddings, right? I'm talking about embeddings, search. How do you actually use them? Use a vector database. So this is how a vector database works. Step 1, you take your unstructured data, you transform it into some sort of vector embedding. So a lot of people ask me things about how do I choose a vector embedding model? It's going to be depending on your data. For example, if you have images, you probably want something like less than 50. If you have text data in the form of sentences, you probably want something like sentence transformers. So the answer is it depends on your model. Once you have your vectors and you transform them and you save them in your vector database, that's all you need to do for saving them into the vector database. Now you can use them, you query them. Your query has to be a vector of the same length as the vectors in your vector database, which means you must use an embedding model that matches in dimensionality between how you transform your query data and how you transform your original data. Of course, I suggest that you use the same model, but it's actually entirely up to you. As long as it matches, you can actually do the semantic search. Once you do the semantic search, you'll get some results. Yeah, that's about how that works. Okay, so why use a vector data? Let me answer questions at the end. I used to let people interrupt me, but my marketing person said you should just talk. Okay. Anyway, why don't you use a vector database instead of a regular database? Let's take a moment to think about how vector search works. Vector search works with primarily 2 different metrics. One is an L2 norm. The other one is an inner product. Both of these are highly computationally expensive. Now let's think about how a relational database, a SQL database, or a NoSQL database works. When in a SQL database or in a NoSQL database are you ever going to have to do any sort of mathematical calculation? Any square roots or anything like that, any squares? Can you guys think of anything? Because I can't. They don't happen. So you have to have a purpose-built, a special-built database architecture to be able to handle high amounts of queries, high amounts of computations. So vector database is kind of different from regular databases in this. Otherwise, they are purpose-built for them. And this slide said for other things, and you can read the slide. I'm not going to read it out to you. Everybody here knows how to read. So the main thing you need to take away is that the architectural difference that underlies a purpose-built vector database is very different from the architectural design that underlies a regular database. So why a vector database? Once again, I'm not going to read the slide. It's a lot of words. You can read it if you want. Just listen to what I'm saying. So a vector database also differs from a vector search library, which you guys may have heard of. Who's heard of Base? Base? Okay, a few people. What about HNSW? A few people. Okay. So these are vector search libraries. So I guess I don't actually need to like sell this slide to you because usually people will ask me about vector search library. They're like, why do I need a vector database? Really, this slide is just to be like, well, you can have a vector search library and you can search over your vectors, but you're going to be missing everything else you need. You're going to be missing the cloud backup. You're going to be missing like, sharding, replicability, multi-tenancy, role-based access control, everything that an enterprise needs to work on a database. Okay, so you can read this. The slides will be available, but that's really what you need to know is that vector databases provide this supporting architecture to vector libraries for vector search. And now I'm going to walk you through Milvus architecture. I just wrote vector database architecture. Really, other vector databases are actually architected differently. I'm going to point out the two main places where they're different. So number one is these kinds of nodes here. You'll see that in this diagram, I've got 3 nodes spun up. From the other open source vector databases, it looks like they're only using 1 node. The reason why it's really good to use 3 different nodes is because you actually have a separation of concerns. So, for example, you don't need to use your indexing node. You don't need to create a vector index all that often. It's like a one-time thing, especially in Milvus. And I will tell you why it's a one-time thing in Milvus for a second. But it's more or less a one-time thing, so it's not very used. And then your data node is more or less for ingestion. If you're constantly ingesting more data, then you'll probably need more data nodes to scale up. If you're just ingesting it once, and then you're going to like query it a lot, you're going to need query node to scale up. So the query node is really the one that we see needing the most scale up. People are often querying their vector databases a lot. So these 3 nodes have these 3 separations of concerns, and that's why they're separated so you can scale them each individually. The other thing that's really cool about Milvus, and this is actually like, I talked to the engineers and I was like, dude, this is like, you guys came up with this. This is smart as hell. They put these things, they put the data into 512 megabyte segments, and then they produce an index over each segment. And then when you're querying, you actually query in parallel over all of those segments. So that's also why you never need to re-index your data. Because re-indexing takes forever. Especially if you have like 10 gigs of data, you'll sit there for like hours, days, just re-indexing. So you never need to do this because you're only indexing over 512 megabytes, and then you're parallelizing them. And I was like, wow, guys, that's a really great way to get over that. And that's why Milvus scales really well. Pop quiz number 7. Purpose-built vector databases are better than traditional ones with add-ons because A, vector search is computationally heavy. B, available hardware acceleration like Milvus's NVIDIA GPU acceleration. Yeah, we have an NVIDIA GPU acceleration I forgot to mention, sorry. And then architectural advantages for scaling vector data, or D, all of the above. I think I saw like someone, like the guy with the gray shirt with the glasses. D. Oh yeah, you're totally right, it is D. Cool. Next one. Milvus. Oh, this one actually is a trick question. Milvus has built a niche in having only one indexing choice, handling billion scale enterprise level amounts of data efficiently, or being a close source vector database, or none of the above. Did I mention this one? I think I mentioned this one, but I want to know how much that means. Yes, guy in my shirt. Oh, yeah. Okay. You were paying attention. That's great. I love that. And that's the last talk. I thought I had 10, but it turns out I only have 8. But that's also the last question in here. FAQ, people will ask me things like, when do you not use a vector database? If you don't need semantic similarity search, if you're just building like a user app, like hey, like I've got some users and I need to make sure they're logging in, I want to make sure that I know what they're doing, you don't need a vector database. Don't bother. CSV files, PDFs. Someone came to my office hours and they were like, hey, like, I'm reading the CSV files, but I'm not getting the results. Like, why is that? And so I said, hey, well, what embedding model are you using? And they were like, well, I'm using sentence transformers. And I was like, well, there's your problem. CSV data does not fit into sentence format, right? It's in comma separated. I don't know what these stands for. PDF. PDFs, you can OCR them into text. They're actually pretty difficult because they have like a bunch of like images and like models and things then. And then hybrid search, people ask me about this. Can I filter on my metadata? Yes. If you only want the results that were put in the last one, you can do that. Role-based access control is in both Milvus and Zillus. We put on Zillus Cloud first, and scaling up and down. So scaling up is a lot easier than scaling down because when you scale down, you have to keep in mind you have to be able to hold your data in memory still. This QR code is a link to a GitHub repo that contains a lot of like example code. So if you want to see anything that I've been building over the last few months, such as how you can do multi-document querying, how you can use llama index, how you can use lane chain, or any of those things, check it out. I've got about 3 minutes up there. And I'm now opening up for questions.
Great thought.
Thank you.
I'm curious how, if you recommend any tools for actually creating the data that you want. So like, if you're a startup and you don't have any data, but you know the data that you want, are there any tools that help you structure data that make it easier to put through that?
Like a bit more specific question about the data that they want.
Maybe more semantic about like dictionaries, sentence structure, concepts, topics.
I mean, usually you would scrape the data from somewhere. Creating data is like kind of a iffy field, I guess. This is like where you could really get in trouble with like data hosting and stuff. If you use AI to create your input data and you train on it, you're like really screwed. So you know, depending on where if your data lists online, that's best.
Thanks.
Yeah, you're welcome.
Just wondering about the like complexity for the querying time.
Yeah.
How much does it scale? Like, what was the approximate nearest neighbors algorithm we used?
Oh, here we go. Actually, this is why this slide has this question. Most vector databases have only one index case. Notice we do not. So you can do IDF if you want, you can do Annoy or support Annoy right now. We might have gotten rid of Annoy. HSW, we have like so there's multiple ones, and you can also quantize it. You can do scale quantizing, product quantizing, depending on how much you probably need. Typically a lot of people like to use HSW, which is a graph-based actually. Oh, okay. Well, I don't have a slide on that, unfortunately, but HNSW uses like a graph-based index, which means that your computation, your creation time, your creation time is a little bit longer, but your memory size is going to be a little bit longer, a little bit larger than the actual size of the vectors, but you will have a very easy query time because all of your relationships are already built into the graph. So it really, the answer is it depends. Sorry.
So I'm working actually integrating Novus right now.
Oh, sick. Okay.
And the question is viability for context management. We don't want to pay OpenAI every time we send a message. How do we rapidly, or is it viable to use Novus to pull in context from sessions? So we're not dumping the entire session in the API.
This is like the whole point of OSS chat. This is like the whole point of like GPT cat is like. So it sounds to me like what you're trying to do is you're taking you have segments of documents and you want to be able to plot the segments of documents that are relevant to you, and then you want to only ask about those segments.
But it's session based. So the session is loaded, stored in the vector database, and then instead of storing that session continuously putting it back in, just having it exist there, and say they send a message that's only relevant to 2 messages they previously sent, save the money, pull the vector, send it off to OpenAI.
Yeah, that's the whole point of caches. Yes, you can do this.
So we're viable. Okay.
It's totally viable and might be tough too.
Yeah.
Yeah. Okay.
Okay. Cool.
Thanks again for the thought.
Thank you.
Really good. So if I understand correctly, the vector database is kind of like memory or cache, right?
It can be used to that.
Yeah. So what about what if like a model training, just like a model drift? How does what kind of problem does it create if the underlying model changes?
As long as the dimensionality. Well, so okay, so there's actually a couple things that you can think about this, right? So number one is interoperability because the data you need is set. And number two is interoperability because you are requiring something different from the model. And I think the answer to the first one is you may not care enough about reindexing because it'll probably be close enough as it is to the proximity standards. But the second one, you might want to reindex. You might want to completely redo all your vector things.
So if I understand correctly, I guess you have to understand your use cases and see like, how long you're going to kind of keep your memory.
Yeah. There's also no way for me to say like this is what you do without like having more context to that.
What if like it's just let's say that the ChatGPT, let's say that I'm using ChatGPT, that model changes over time, like 6 months later, something. Does it create any issues with your vector data?
I mean, like not in functionalities. Yeah.
I actually have two questions.
Sure.
One, you mentioned one benefit of the case of vector DB is the sharding. Can you explain that? a little bit?
Yes, okay. So she asked about why did I say something about sharding with vector database? Like, what do you mean sharding vector database? What do you mean sharding the database, right? Well, actually, we have read ahead, so we have Kafka and Pulsar. And so as data is coming into the segments, we actually use Kafka and Pulsar as our read ahead log. And we get the data from the data streams if we are working on a growing segment. A growing segment is a segment of data that has not yet reached 512 megabytes.
The second question, I just would be curious how you query the vector DB. I suppose it's not a SQL language. I'm really wondering, like besides calculating difference or similarity between, let's say, index dependence, right? What else you can do? Can you answer like what's the probability of the substituting words from a given search word? Anything like that?
That would be a question.
Yeah,
for
example for the current language, I would like to say.
I can show you the query. Actually, if I'm just going to pull this back up, if you scan the QR code, it will take you to the examples.